Okay. Can you see my screen?
Yes, sir.
Yes, sir.
So you may all know where the base plates are used. So if you have a wherever you have a column, so for example, you may have a industrial shed like this, and these are the columns. Then the columns are connected to the foundation, right? And right at this interface where the column is connected to the foundation, you have to provide some kind of a base plate typically. Okay. There can be other ways to provide this connection wherein, so typically if you look at a pole, for example, electric pole, okay, so they usually don't have this kind of a base plates kind of a setup. They have a more of an embedded kind of a setup. So they have a they dig a trench or a hole in the on the ground, and then they basically kind of create a formwork, okay, and put the pole and pour concrete in that formwork, so which surrounds the pole. So that is a typical way which is used for poles, but there is a limited the load values are not that high, and plus so therefore you don't need a very heavy duty foundation. But wherever you have a proper foundation design for this purpose, that foundation has to be connected to the column appropriately. So typically that is the purpose of a base plate. It is used to connect columns with foundation. Okay, so they should be able to transfer all the axial forces, bending moments, and shear forces, right? So you can see this is the axial force P, this is the shear force, and this is the bending moment. So all such requirements might be force requirements might be there on the foundation or on the column base, and that has to be transferred to the foundation. So this is a typical detail of a base plate. What is what here? So this is your column. Let's say it's a structural steel column, right? So this can be an IS column section. You're familiar with some of the IS column sections or ISMB section. So this could be one of the column sections with parallel flanges. Okay. So this is that section, and then at the base, it is capped with a base plate. Okay. So basically, in a 3D, I'm sure, yeah, here. So what you see here is this is the column, and this is the base plate. The column is connected to the base plate through welding. So either you may go for a fillet weld. So what you see here are fillet welds. You all know what fillet welds are, right? So whenever you have two perpendicular surfaces, this could be the column and this is the base plate. Here you get a perpendicular surface, right? So if you put this triangular shaped weld, this is called a fillet weld. Okay. The other alternative could be to go for a groove weld. So in that case, you had a column which was coming out like this. You may simply, if the column plates are very thick, you may cut a groove in these column plates, and then you have the base plate, and then you can fill this space with a weld material. And typically, when you go for this is called a groove weld, okay, or butt weld. So when you go for a groove weld kind of a system, it is always preferential to go for a full penetration groove weld. So basically, what you are doing is you are substituting the base material in a way with the welded material. So as long as your weld material is stronger than the base material, you don't have to worry about the geometry and strength, because basically the geometry of the weld is almost similar to the base material. Okay, so this is called a groove weld. So either you go for a full penetration groove weld or you go for a fillet weld. Since now we are talking about only compression members, so when the compression only will be applied, in that case, generally this weld strength does not play a very significant role. So there can be some minimum amount of nominal welding you may do. You don't have to really design the weld, as long as you are getting a full contact between the column end and the base plate. So as long as your base plate is perfectly flat and the column end is also machined to be perfectly flat, that means the entire column cross section will be bearing against the plate. Okay. If you don't machine them, and generally these sections, big sections, are cut with a gas cutter. So if that is the condition, then what will happen is that your column ends will have this kind of undulations. Okay, and then there is a base plate sitting under it. Right? So base plate has this flat curve, flat line, and then column end has this kind of undulations. Then you will not get a throughout uniform bearing. Okay, so that is not a good approach. Then in that case, if you cannot machine the column end, at least it should be better than the gas cutting surface, but still then you can weld it. And the weld, then in that case, the weld has to be designed to carry that entire load. Okay, so you may have this I section, which all the edges have to be welded. You may have square section or a round section. All the edges have to be welded all around. Okay, then you have this base plate, which is also a steel plate. Then the base plate has to be anchored into the foundation, that is pedestal, right? So that whatever foundation you may have underground, that will be coming up at the top, whatever shape or form. And then you will be having some kind of a pedestal at the top, right? After the foundation. So that pedestal, these anchor bolts will be going into this pedestal to anchor the base plate into it. So these are called nut and washer. This is anchor rod or anchor bolt. Okay. At the ends, typically we do a this kind of a nut we leave, or otherwise sometimes we use J anchors also, and these have to be installed while the pedestal is being cast. You can do it otherwise also later on also. For that you have to drill a hole, and then you have to use some kind of an epoxy or a grout which is proven to work against this kind of a shear capacity. So you should know what is the capacity of that one for that particular binding material. Otherwise, if you don't want to go through all that hassle, you have to provide these anchors while you are casting the pedestal. Okay, so all these, especially what you need is you need to know the locations exactly where these holes are going to come beforehand when you are casting the pedestal, so that your anchors are exactly at the right location. Because even if they are off by 5 millimeters or so, then they will not fit into the holes into in this plate. Okay, so these are anchor rods or anchor bolts. Of course, you need nut. Sometimes you may just provide a nut at the bottom also to provide that additional anchorage. Then what happens is that usually this base plate does not come all the way to the top of the pedestal, because pedestal surface is not perfectly flat. It is a typical concrete finished surface without a formwork. So without a formwork, you will not get a very smooth surface. So what we do is we don't bring the base plate all the way to the level of the pedestal. We leave some gap, and that gap should be big enough so that we can. Sorry. Yeah. So this gap between the base plate and the pedestal should be large enough so that we can fill it with grout. Okay. Usually you should go for a low shrinkage grout. Why low shrinkage grout?
To avoid the shrinkage. Right?
Yeah. What's the problem if there is a shrinkage?
There will be a.
I mean, the base plate will not be. I mean, exactly.
Uneven settlements will
settle.
It can settle.
Settlements.
Differentially, I mean, if it is uniform,
Yeah.
then no
So yeah,
problem.
so basically
The differential settlement.
Differential. I mean, see, this is, let's say if it is 1 inch and if there is a shrinkage, it is not going to cause a differential settlement to the building. Like how much will be the shrinkage strain typically? So that is not going to be differential settlement problem. It is going to have a loss of contact. Okay. So as soon as this grout starts to shrink, and if it shrinks by large enough amount, you will have a crack surface here. You can call it crack, or you can call it a delamination, and you will have a loss of contact. Okay, and then you will have this grout cracked all over. So it will not be stable there. So as soon as the cracking, once this grout has cracked due to shrinkage, because it is not confined very well from all sides, it is just sitting there. So once it loses contact with the top surface and then it cracks inside, then it will not provide the resistance against corrosion. It will keep water, allow water to seep in. All kinds of issues will arise. And also it will slowly, with vibration, if there is any vibration kind of a loading, chances are that this will start to move around. Okay, and it will not be effective. And what we need it for, this grout should be high enough strength so that it resists all the force that we are designing this foundation, this base plate for. Okay. So that's why we need low shrinkage grout typically. But you will often see that regular mortar, as long as this thickness is not very high, even regular mortar also works. You will often see that there people using this regular kind of a mortar. Okay. Then of course you need on this anchor board, you have to have threads wherein you can put these nuts from the top to tighten the whole thing together. Seldom you would see something of these anchor rods are seldom high strength. Usually they are normal strength steel, usually 410 MPa. Okay, steel, regular steel threaded rods. As far as compression is concerned, compressive loadings are concerned, these anchors don't have much of a role to play as long as they just hold the column in place, because we are assuming that there is no lateral load or no significant lateral load, or there is no uplift force, that is moment demand. As long as that is true, these anchors, we don't have to really design the anchors. We can go for the minimum requirement by whatever is available or whatever is the common practice or makes sense. Okay. Yeah, so this we have covered. So typically, how does the design go? So basically, the purpose of a design of a base plate for pure compressive conditions is to just make sure that two things don't happen. One, our concrete under the base plate does not crush, or if it is grout that we are putting, that grout has certain strength and that grout does not crush. Okay, that is one. Usually we make sure that grout is of higher strength than concrete. Okay. Second one is that the base plate itself does not fail. And in what way can it fail? We will talk about that. Okay. So when we are talking about pure compression here, for example, if you take a look at this picture, if it is pure compression, there should not be any strong reason for the base plate to fail. But what happens is that if the base plate was only of this size, okay, then we could be pretty much sure, and as long as with this size base plate we were able to make sure that concrete does not crush, the base plate should not fail. Because if concrete, which has, let's say, crushing strength of 20 MPa, if concrete is not crushing, the base plate would definitely not fail. Okay, base plate is much stronger than that. But usually that is not the approach, because what we have to do is, in order to make sure that concrete does not crush, we have to extend the base plate. So base plate is often always bigger than the column. Okay, so column cross section is only this much. The base plate is extending beyond it. It has to be extended. Also, you need a place to put the anchors. So for that reason also you have to extend it. So once you extend it beyond the column cross section, then what happens is that your stresses or the forces that are acting on the base plate are not really perfectly face to face. They are applied at an offset, and that causes some issues. So first we will talk about this problem of concrete strength or bearing strength of the concrete. Okay. So what happens is that you can understand that concrete will be under stress, and there are two different codes which you can refer to. If you refer to IS 456, it says the bearing strength of concrete is should be taken as 45% of the FCK value. The IS 800 says it should be taken as 60% of FCK. So we can typically be conservative, because we don't know whether we are dealing with steel design here or concrete design here. Okay, so we can be conservative. We can take 0.45 FCK, whichever code is giving us the smaller value. Okay, we can use that smaller value. And from there, we can calculate how much is the minimum area that we need to have for the base plate. So the area under the base plate can be given as whatever is the factored loads, actual loads acting on the column, divided by the strength of the concrete. And that should be the area of the base plate, minimum area of the base plate, which is straightforward, right? So if you had this base plate, this is the size of the base plate. So you take the total load PU, factored total load already has all the factors added, total pure compressive load, that divided by A. So PU divided by A should be less than 0.45 FCK. Okay, makes sense, right? Going forward, now comes the question of how to make sure that your base plate itself is safe. It can be called a base plate, or sometimes it is also known as slab plate or base slab. Okay. So this is basically a steel plate, and let's say you have a cross section, this column cross section, which is sitting on this base plate in this way, and your column size is BF by D. D is the depth and BF is the width. Okay, and let's say your base plate is extending by A and B amount on the two sides on the respective sides. So the base plate dimension will be taken as L by B, wherein L will be equal to D plus 2B, 1B here, 1B here. Okay. And similarly, your B will be equal to BF plus 2A. Okay. So this will be the typical area that we can take for the base plate. However, one has to be careful, because if you go to IS 800, here it exactly gives you how to calculate the actual bearing area. Okay. So the idea here is that if you have this cross section, for example, you start moving away from the edges uniformly in all directions. Okay. So let's say you move by amount C in this direction, then you move by amount C in this direction, you move by amount C in this direction, likewise. In every direction, you move by the same amount. Okay. And keep calculating what is the total area you are getting. Once that area satisfies your requirement of PU divided by 0.45 FCK, that is your minimum area requirement. Okay, you get it? So that shape will basically depend on the shape of the I section that you are dealing with. Okay, and this particular respective C will be C. Now, basically what this tells us is that this is the minimum size of your plate. So likewise, you get the value of C. For that value of C, you draw a rectangle. This will be your minimum C, or minimum area of the plate. Now, either you can provide a plate in such a way so that it has an edge meeting with that C here, or you can provide your plate in a way so that it meets that edge here, or you can provide it in a way so that it doesn't meet anywhere. It is bigger on either side, on both sides. Okay. So all these three are acceptable options, but you have to make sure that your area that you are calculating, that you are using in this calculation, okay, is actually only this one. With this area, you should be able to satisfy this requirement. So this is actually, in fact, slightly wrong. This would be true if these two things meet together and you cover the entire area. But ideally, you should do this calculation. Okay. So this one, I think I'll revise and I'll upload the presentation again. This is based on some of the international codes allow you to do this, but as per the Indian code, you should take this area and satisfy this requirement, U by 0.45 FCK. Okay. Now, once this stress requirement is satisfied, you know your base plate size, right? So, for example, in this case, the minimum base plate size is this much, and then you can decide to go for a bigger base plate like so, or like so, or like this. It doesn't hurt to provide a bigger base plate, but if you provide a bigger base plate, you have to be careful about the thickness of the base plate. Okay, fine. This part is clear. So let's say you provide whatever size base plate you do, then you have to make sure that the plate thickness is sufficient. Okay, so how do we do that? Now, why should the thickness have a role to play? What is the factor that controls the thickness of the plate? So if you may notice, this is the area that is supporting the actual column. Let's say this is the web and these are the two flanges. This is the area that is gray area that is actually supporting the column. Now, the base reaction you are getting everywhere. Okay, and as a consequence, but your compression up downward load is effectively acting here, or you can say it is distributed only in this region, in this gray region. So whatever area of the base plate that is extending outside this gray region is basically under eccentric loading and will be subjected to some kind of a moment demand. Okay, and that moment demand should not be large enough so that it makes the plate fail. So for that, you have to design this plate. So for example, if I have this base plate and this gray area represents the forces that are belonging to the column, that is downward force on the base plate, and the upward reaction is coming from everywhere throughout the cross-section area of the base plate. Now, if you look at this, this is the gray area, this gray part, this entire area is this much. Okay, and your base plate is extending by 2B. it is extending by 2b on both sides of the loaded area. Okay, and then let's say the reaction is W. Reaction is calculated as W, and this W will be equal to total P, that is total PU coming onto it, divided by A divided by B. Okay, total area of the base plate. So this W should not cause, I mean, of course, it will cause some moment here, but this moment demand, you can understand this is almost like a cantilever, right? So this moment demand at this fixed end of the cantilever should not be too large so that it fails. So it should not fail. Sorry, the plate should not fail. The plate should not plasticize. Okay, so how much will be the moment demand? We know if we know the distributed load is W, then W multiplied by B square divided by 2 will be the bending moment in a strip. Let's say this is that strip we are looking at. This is the length of that strip. We have aligned that particular strip this way. So this was the length B. Correct? This was that length B. So over that length, the load is acting everywhere. The distributed load from the pedestal is acting everywhere, that load W. So WB square by 2 will be the bending moment demand at this point. Okay. At this point. Now, basically, we have to make sure that this moment demand is within the capacity. Now, the problem here is that if it was a uniaxial kind of a bending, then this would have been true. But what happens here is that if you look at, so in one direction, you have this WB square by 2 moment coming on at this edge because of forces acting on this strip. So if you look at this particular part, the moment direction is this one, okay, because of these forces. Right. But at the same time, this strip is also extending here, right? And this strip is also having a moment. Correct? Now, what we have to do is we have to make sure that we have to design it for the two considerations, for the moment here and for the moment here. And funnily enough, what you can find is that the moment in one direction actually helps the plate resist the moment in the other direction. How does that happen? We all know that if we have a steel plate acting under uniaxial bending, right? That is one-way bending, right? You might have all heard of one-way bending. So if you had this straight plate, so this was a plate to start with, straight plate. A straight plate that if you apply some kind of one uniaxial bending moment or one-way bending moment, okay, it will undergo this kind of a bending, right? Which will basically, it will turn into a kind of a cylinder instead of a plate, right? That's what we expect. Fine. And that is true if we do not account for the Poisson's effect. But if you now look closely at this, if I take a strip of this plate and look in this direction, I'm looking into this plate in the thickness way. Okay. So this was my plate to start with. That is this strip I'm looking on at this thing. This was this square. Okay. Once it undergoes this kind of a bending, this part is contracting and this part is expanding. And if I include the Poisson's effect, the part that was contracting will actually laterally, it will expand. Okay. And the part that was in tension, it was stretching. So it will, in lateral direction, it will shrink. And as a result, I will have a strain gradient in such a way so that this part extends in this direction. So in out of the bore direction, it is contracting, but in out of the plane direction, it is contracting, but in plane direction, it is as a result of Poisson's effect, it is expanding. I'll say C and E. E for expansion, C for contraction. Similarly, in out of the plane direction, this was expanding because of the way we are applying the bending moment. But in this direction, it is going to contract. Okay. Now this expansion and this contraction is in the other direction, right? So in the direction where we might not even be applying any bending moment. And even in that direction, what you can see is that actually we are applying bending moment only in this direction. This is same as this. But because of this expansion and this contraction, what may happen is that bottom one is contracting, right? So you will have a bending going on in the perpendicular direction too. You understand? You understand that, all of you? Because of the Poisson's effect. So without the Poisson's effect, you can have this kind of a deformed shape. Is the class present even? Hello?
Hello, sir.
Yes, sir.
You guys are following, right?
Like I do
Yes, sir.
once more explain this.
Yeah, I'll try to explain again. So if this was a straight plate, let's say, and we apply bending moment in one direction, okay? So you expect it to bend in this direction, right? That's what I'm showing here. So instead of a plate, a flat plate, it becomes a cylinder. It deforms into a cylindrical shape. Okay. By cylinder, I mean it has a curvature in one direction, but the other direction it is straight. So this line remains straight. It has curvature only on this axis. These are the two axes, right? X, Y. So in the X direction, it does not have any curvature. It has curvature only in Y direction. That's how the moments were acting. That is okay as long as you ignore the Poisson's rule, Poisson's effects rule. If you include the Poisson's effect rule, what will happen is that since I'll erase this just to keep it out of clutter. Because of the Poisson's effect, let's cut a small square from here. It has certain thickness, right? So I'll cut a small square from this thickness and I'll look at this square. Okay. Now in this bending, the top part of this square, is it under compression or tension?
Compression.
Compression.
That means, yeah, it is shrinking or expanding?
Shrinking.
Shrinking. Okay, so I'll call S shrinking. And the bottom one, it is shrinking or expanding?
Expanding.
And this shrinking and expanding is in the plane direction or in out of the plane direction? For this figure?
In plane direction.
No. See, this shrinking is basically in this direction, right? And now I'm looking at this particular square and I'm looking at that square here. So whatever movement that was happening, at the top it is shrinking, at the bottom it is expanding. But now for this square, it is in the out of the plane direction. So this shrinking, if I can draw this, it is shrinking in this plane and it is expanding in this plane, the out of the plane direction. But I don't want to draw all that. Fine. Everybody follows that this shrinking and expanding is an out of the plane direction for this one?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Fine. So now if it is shrinking in out of the plane direction, I'm compressing it in this direction. Okay, I'm compressing it in this direction. What will happen in this direction and that direction? In this direction, what will happen? So if I'm compressing it in this direction, that is the way to show compression or inward movement. So what will happen in this direction? Because of Poisson's effect, it will expand in this direction. Correct? This is the way to show. Okay. So in this direction, it will expand. Similarly, since it is expanding in this direction, in the lateral directions, it will shrink because of Poisson's effect. Okay. So now the shape of this thing will actually change. Okay, so which basically means that, let me again mark it. let's call it X, let's call it Y. So now X direction is in out of the plane direction, and Y direction is this one. Okay. So in the X direction, I was introducing the bending moment in such a way so that there was expansion and contraction in the X direction. But because of the Poisson's effect, now I've got expansion and contraction in the Y direction. That means there is a bending introduced in the Y direction also. Okay, the top layer, this is the top layer, it is expanding in the Y direction, but the bottom layer is contracting in the Y direction. Okay. No?
Yes, sir.
Yes, sir.
Yeah. So bottom layer
Yes,
is
sir.
contracting and top layer is expanding in the Y direction. And as a result, you will have a bending. So now earlier, if you were ignoring the Poisson's effect, you had a straight line here. But actually, because of this Poisson's effect, whenever you apply bending moment in one direction, you will have a bending going on in the other direction also. This one. Okay. How much will that be? That bending moment will be the WB square. Let's say I am applying WB square by 2. So in this direction, I have a bending moment of WB square by 2. That is the bending moment at this point. But that bending moment will cause a bending moment in the other direction that is equal to 0.3 times WB square by 2. That is Poisson's ratio. Okay. You understand, right? So if there is any movement here in the perpendicular direction, it will have 0.3 times that movement. Therefore, you have 0.3 times WB square by 2 bending moment. This is clear, right? WB square by 2. And from that, you get in the perpendicular direction, you have a bending moment of 0.3 WB square by 2, but in the opposite direction, right? So for example, now I look at this again. So if you had this length as B, this is B. Okay. So the bending moment of this strip at this point, this bending moment was WB square by 2. But because of this moment, because of this strip, there will be a moment, or because of these forces which are acting on this strip, there will be a moment in this direction also, which will be opposite. Okay. And that will be equal to WB square by 2 multiplied by 0.3. Okay. Which is basically corresponding to the moment which would be on the orange colored strip. You can see this orange strip. So it is the same direction. But this moment WB square by 2 multiplied by 0.3 is coming from the moment on this one. Okay. So basically, if I want to calculate what is the actual moment here, if I want to calculate total moment here, so one moment will be, let's say this length is A. So one moment will be WA square by 2. But the other one, so WA square by 2, of course, is coming from the forces that are acting on this strip, this orange strip. But the forces that are acting on this strip are also causing a moment in that direction, and that is 30% of WB square by 2. Okay. I can take W by 2 as common. I'll get A square minus 0.3 B square. If you don't want to do all this, you can also, you will only be conservative. If you want to ignore this effect, you can simply ignore this effect. You can say WA square by 2 is the moment demand. Okay. That is also okay. That will be more conservative, and some codes allow you to do that. But Indian code requires you to calculate this effect, Poisson's effect. Now, this was the moment demand. Moment demand, if I know the W, and you know the W already, right? W is basically equal to PU divided by AB. So if you knew W, from W value, and of course you knew A. What is A? A is basically extension beyond the column base. So A is this extension and B is the other extension. So in the two directions, you will have A square minus 0.3 B square, or B square minus 0.3 A square. And whichever one would you take? You'll take the bigger one. So which one will you give? If A is bigger than B, then A square minus 0.3 B square is going to give you the bigger value. Okay. So that was the moment demand. Now the moment capacity for a plate. If you have a plate, and again, we are taking a unit thickness. Okay. Likewise, we took a unit thickness here also. I never mentioned in this entire calculation. This W is the per unit area force. So what is the width of this strip? I never mentioned the width of this strip. This was unit width. Okay, 1 millimeter you might assume. So these strips are 1 millimeter wide. Okay. Now, what is the capacity of that 1 millimeter wide strip? Moment design capacity of in moment. We know it is all S multiplied by Fy, right? S is the section modulus multiplied by Fy divided by gamma n0. Now this S is basically your elastic section modulus. If you want to design for plastic limit state, which is we are allowing the entire cross section to plasticize, approximately you can take it as 1.2. Okay? So 1.2 times the section modulus, that should give you approximate plastic section modulus multiplied by Fy divided by gamma n0. Okay. Now we can do the rest of the calculation. S is nothing but I divided by T by 2. T is the thickness of the plate. What are we trying to do here? This was the strip of the plate. This was all W acting here. This was, let's say, fixed here. And we want to know what is the moment capacity of this plate. We want to know what is the moment capacity of this section that I'm coloring right now. So how will we calculate that moment capacity? We are talking about moment capacity in this axis. So T is the thickness. Width I have assumed to be unit. Okay. So S will be equal to I divided by T by 2, and I will be equal to 1 by 12 BH cube. So B is 1 and T cube, that is T cube. I can take 1 by 12 T cube, that I am substituting for S, and divided by T by 2, gamma n0. Okay, which is equal to, I'll solve it further, it turns out to be T square Fy by 5 gamma n0. Now if I equate the moment demand with the moment capacity that I just calculated, I can find out what is the minimum T. My T value can be calculated as per this equation. Okay. Now, in addition to this requirement for T, we also have to make sure, that is as per the Indian code. If you go to clause 7431, you will see that this thickness of this plate, base plate, should be more than the thickest plate in the cross section. That is flange thickness. So if you have an I section, if I have an I section like this, so you have this plate thickness, right? So this thickness, this is, I can call it T slab, and this will be called T flange. So T slab should be more than T flange. Okay. So first we do this calculation. First we solve for T here. For solving for T, what do we need? We need W. We need to know Fy of the plate, and we need to know the dimensions of the plate that is extending outside the column cross section. Once we know those, we can calculate the required thickness, and then the base plate has to be thick enough so that it is more than this and it is more than TF. Fine. The idea for the plate to be more than TF is so that it does not cause a punching into the plate. Okay. Then, in addition to the base plate, we need to provide anchor bolts, and anchor bolts should be 2 to 4 in numbers. As long as forces are purely in compression, the anchor bolts requirement is not very specific. Whatever is the conventional, whatever seems okay, you can provide. Usually, at least 4 are provided. 2 is still too low. So always we go with 4 anchor bolts. But it is a hypothetical condition. For most of the columns, you will have some kind of a shear force demand or bending moment demand, and the anchor bolts have to be designed for that bending moment demand. Okay. In addition to that, a proper grouting is very essential under the base plate. Between the pedestal and the base plate, you have to do grouting before you start put this thing in service. And also full penetration or sufficient strength fillet welds have to be done between the column and the base plate that I have discussed already. Okay. If the loading is eccentric, then it goes into the domain which is almost like into concrete design. Basically, what happens is that as long as you are doing this weld, this could be a groove weld like here, like I'm showing, or it could be a fillet weld like I'm showing here. So whatever type of weld you are going with, that weld has to make sure that it is stronger than, that weld is stronger than the plate itself, the member itself. Okay, so it can resist the entire capacity of the member. That is one part. In addition to that, whatever you have to do, you have to provide the anchors. Now, anchor design is mostly considered within the RC design. So I don't know whether this will be covered in your advanced RC class, but all the codes do mention how to design an anchor for concrete, because when anchor fails, typically it is the concrete that fails. So we have to design the anchor depth, etc., and diameter, etc., based on the concrete failure. So anchors have to be designed. And also, when you design the base plate, then basically for that base plate design, what happens is that your reaction from concrete here, for example, if you are under bending moment kind of a condition, so you have normal force acting and you have a moment. When you have a moment acting, your anchors also have to be designed for the tensile force demand. So usually that's how the anchors are designed, because you will usually have some kind of a bending moment demand. That force you have to worry about. Plus also there will be bearing stress, and that bearing stress, usually the way we do it, we design the base plate in such a way so that the entire concrete crushing strength could be applied, and then the base plate should be able to resist that. Okay. But where the neutral axis exists on all those things, I think there is a separate chapter on that one. I don't want to go into that topic. The idea is that base plate, the concept of designing the base plate still remains the same, that whatever moment you are applying to the base plate, it should be able to resist without completely plasticizing. Okay. So that is your bearing stress you have to worry about. So this FB multiplied by this FC, if I may call it, concrete and bolt. So FB and FC, they are couple, if you may say so. So FC would be a net force acting downward, and FB will be the upward force. The net couple of these two forces will be the bending moment capacity. Okay, and as a result, whatever stress requirement you are getting, that should not exceed the bearing strength of the concrete. Anchor strength, of course, again, because this FB should be less than the strength of the anchor. Now, anchor strength itself depends on two things. It's minimum of the two. It is the yield or fracture strength of this anchor itself, and also it is the pull-out strength of the concrete here. Usually you have this kind of a pull-out wherein this concrete comes off along with the anchor. So the anchor strength has to be sufficient so that it can provide all this FB force required and shear resistance. Anyway, this is not, I'm just giving you a brief overview. You don't have to, as a part of this course, you don't have to learn how to design this. And often what happens is that this bending moment demand for the base plate turns out to be so high that this kind of a base plate design does not work. And we have to go for some kind of a stiffener system. So we do some kind of a stiffeners we provide in addition to the regular base plate. And this is often required when we have this kind of a eccentric loading. Okay. So this is often known as gusseted base plate. Okay. So with this, I think this chapter concludes. I can take some questions.
Sir, when you said no, sir, in steel generally we will go for the concrete foundation, but somewhere I heard that Grillage foundations are also used. Do they really use now, or
which foundation? Can you repeat?
Grillage foundations. In the bottom one they'll lay the steel beams in both transverse directions.
Okay. At least in India, I have not seen it used very much. I don't know how often it is used. Yeah. Anything else?
Excuse me, sir.
Yeah.
So actually, between equating the moment demand and moment capacity, we take the rectangle section, so the shear factor is 1.5, so we take 1.2.
Actually, that's a conservative one. So yeah, shear factor for a rectangular shape is 1.5. So that is basically, ideally they should have taken 1. Why do they allow the base plate to yield at all? But they are taking as 1.2. That is what the Indian code does. Okay, it's try to be conservative, I suppose. They don't give the explanations why exactly they are going for 1.2 instead of 1.5, but.
Okay, sir.
Okay. Yeah. Anything else? Okay, then I think I will conclude this class in that case. We'll finish this early, half an hour early. Okay. Any questions with respect to the project or something? With the exam, we have to decide. How are others taking the exams for this course? In the, I think ASM course, has Dr. Madhavan taken the exam yet? Advanced Structural Mechanics.
No,
He has not taken
No,
the
sir.
exam yet.
No, not yet. Not yet. Sir.
Has anybody taken an exam?
Yes, sir. In elasticity, we had 2 exams, take-home exams.
Take home
Another
exams.
one,
Okay.
yeah. Another one we will be having tomorrow, I guess.
In elasticity course itself. Okay.
Yeah. That's
Okay. So that is mostly written like long exams to solve, or it is objective type mostly?
no, sir. It's mostly theoretical, problematic.
So mostly numerical, or you have to derive something?
Both, sir. Numerical and derivation also.
Okay. Okay. I'm still wondering. I mean, what kind of format do you guys prefer for the exam? Please suggest something. Take-home exam is better, or I give you an objective kind of Google form I float, which you can fill in within a given time. All of you need to have good internet access for that.
so take home I think is better.
Yes, sir.
Take-home is
Take home.
better.
Take home, sir.
Okay. Okay, fine. So I'll work out something. We will fix a time, maybe on a Saturday or something, to conduct the exam. Like, it will not be fixed hours anyway. I'll upload the question paper and I'll give you a Saturday to work on it, and then you can submit. I'll give you a day or two. Usually they're giving at least 1 day, right, to complete the exam?
Yes, sir.
Upload it. Okay, fine. Yeah. All right. Any other questions? Anything to discuss?
So when will you like keep this exam, sir? Like next week?
When do you want?
Not this week, so yes.
Okay.
Actually, a lot of exams.
You have a lot of exams? Okay. So fix the date. It's actually better if you fix the date now. That is actually good, because otherwise it keeps getting postponed till the end of the semester.
Or instead of that, you can go for objective exam. I mean, it will be finished in 30 minutes, something. Or
Yeah, whatever you guys like, you tell me. Correcting is very easy for me for the objective exam. It takes me some time to prepare the question paper, but correcting is very fast. So, but whatever you guys prefer, you tell me, majority.
So next weekend is fine.
Okay. First of all, the format. So you prefer the take home kind of a comprehensive, like theoretical, for not theoretical like that. There is not much theory here, but like proper pen paper type of exam, right?
I prefer objectives.
Okay. Others?
Yeah, objective.
Okay, you guys, I don't know if I can take a poll here live. Is there a way to take a poll in this one? I don't think so. No. In the chat box, please message quickly. What type of exam do you want? Objective type or a pen paper type of a exam?
So for both the exam duration will be same?
No. If it's a take-home exam, I'll have to give you at least almost a day. Or if I upload it in the morning, I'll give you some late in the evening deadline. Objective type will be very, very restricted, like half an hour, 45 minutes, something like that. So I'll upload the question paper. I'll tell you the time beforehand. Once I upload the question paper, immediately within 40 minutes you have to solve it. Wow, it is neck and neck. 1, 2. Okay. Why is anybody keeping count? I think they are still almost neck and neck.
Equals 7 and 7.
Yeah, 7 out of 15, I think. Objective is 7 out of 15, isn't it? 3, 4, 5, 6, 7, 8. Oh, 8 objective. 1, 2, 3, 4, 5, 6, 7. Okay, so objective wins. Anybody else wants to vote yet? I don't think there are anybody else. Okay, then objective it is then. My worry is that others who have opted for take home, do you have good enough internet that you can solve the question paper in 45 minutes? Because then the majority may not matter. If somebody says that I didn't have the good enough internet and you gave me like 30 minutes only to. Huh? Anybody has that issue of internet?
Then I'll change it to take home. I'm facing some issues right now.
Okay.
Yeah, I want also take home, sir.
Okay, fine. Then we'll stick with the take home type of an exam. Fine. So then I'll upload the question paper. When do we do it? Fix the date now. This Saturday you don't want it, right?
Yes, sir. Not this Saturday.
Next Saturday?
Yes, sir.
Okay. So next Saturday is your exam. Okay. Mark your calendars. I'll upload the question paper hopefully on Friday or Saturday early morning. Okay. And you have to complete the exam before 9 p.m. Upload the exam before 9 p.m. on Google Classroom. Six 1 3 2. All right. Also, I don't know when you guys will get the request to give a feedback. Usually what happens if I teach the first part of the course, then people forget by the end of the semester what the feedback, like how was the teaching or how was the total experience. I would like you to give a feedback. So, but you would not have gotten any request for submitting any feedbacks yet, right? That will come only towards the end of the semester.
We did not get anything, sir.
Yeah. Okay. So I think now it is required you to Lohit, do you know if is it required to submit the feedback to see the grades?
No, sir. I mean, earlier it was like that. If you submit the feedback, then only grades will be announced, and that too within the deadline you should be submitting. Like for 1 to 2 segment, within the 1 to 6 segment deadline, you have to submit the feedback. Now they have changed it that whether it may be 1 to segment or 3-4 segment, you can submit the feedback up to the deadline of the last deadline of the coursework. So, but there is a problem that if you won't submit the feedback, then you can't
See the grade.
Yes.
Okay, fine. Okay. So now I don't have to worry. Now you guys will submit the feedback. Earlier, what was happening was that students, especially if I had taught in the beginning of the semester, students were not very keen to submit the feedback. So I was not getting any feedback from for most of the classes I was teaching. Because I was the first one to teach many of the classes, especially for undergrads. PG classes are still okay. Students are more responsive. Okay, fine. So yeah, please submit the feedback. All right. So best of luck. Best of luck for the project. You can still contact me if you have any questions before the exam or before the project submission. Project submission is due on Tuesday, right? Or Monday?
Monday.
Okay. Let me know if you need more time. I can give you a couple of days extra if you need to.
Okay.
All right. Fine. All right. Best of luck. Bye-bye.
Thank you, sir. Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Yeah.